Hi, this video lesson is going to be a continuation from the previous on circular motion, where we looked at tangential velocities. This one is going to pick up looking at centripetal accelerations. Now, before we get into some of the new stuff, here's a diagram that is going to help just recap and refresh what we had previously looked at. So the green vectors on this circle are representing our tangential velocity. The blue is representing the radius, and then obviously the red circle here. Now, what we notice is that the tangential velocity with respect to the radius, as they are both measured, actually forms a right angle, which is fairly interesting. But again, notice how the tangent line is representing our velocity, because if the object were to no longer be in circular motion at that exact point in time, the tangential velocity is going to tell you where that object would then fly off to. Looking at our acceleration here, again, our definition for acceleration is delta v over delta t. It's our change in velocity over our change in time, where the unit is meters per second or meters per second squared. So that still hasn't changed. What is going to be a little bit different about our acceleration here is which one of those is changing, right? Which part of the velocity is changing? Because as we already know with our tangential velocity, that is going to be a constant speed as it moves around the circle, which then tells you that the direction is what is actually changing. If you watch the simulation on the right-hand side here, as this ball spins around the circle, the speed of that ball stays constant, but by definition, it is accelerating because its direction is constantly changing. If you take your tangent lines, and if you draw a tangent line right now where that red ball is at, and if we were to play this for another 0.2 of a second and draw the vector for our velocity, the vector length would be the same, but the direction would be pointing elsewhere. That's how we know we have this constant acceleration. Now, this acceleration is referred to as a centripetal acceleration. The word centripetal means center seeking, right? So the acceleration is pointed towards the middle of the circle. No matter what the orientation is, the centripetal acceleration is always going to point towards the center of the circle. Our velocity is always going to point tangent to the circle, and this acceleration and velocity being at 90 degrees with one another, that's what causes the curvature. Again, thinking back to projectiles here, the horizontal velocity is one direction, the vertical acceleration is at 90 degrees to it, and it causes that curvature. Same idea here. Velocity and acceleration are perpendicular to one another. We get curvature in the motion. But this time, there's nothing to hit, right? So it just keeps spinning and spinning and spinning and spinning. Unlike with free fall motion or projectiles, eventually it hits the ground and there's nothing for it to wrap itself around. So our velocity is constantly changing, but our acceleration is always pointed towards the middle. Again, look at the velocity vectors on this diagram. They're changing directions, right? Every 90 degrees on that circle, we're seeing that vector pointed in a different direction. The acceleration always towards the middle of that circle. And our acceleration we can find in two different ways. Our centripetal acceleration is either the square of our tangential velocity divided by the radius of the circle, or it is 4 pi squared times the radius of the circle divided by the square of the period. So we have two different ways with which we can find our centripetal acceleration, which is actually quite handy. So we're going to get a couple quick examples here. So we have 4 parts of the example. You spin a yo-yo on a 3-meter string at a linear velocity of 36 meters per second. How long does it take the yo-yo to make one full revolution? What is the centripetal acceleration on the yo-yo? The next example, you want the same yo-yo to travel 1 revolution every 2 seconds. At what tangential velocity is it moving? What will the centripetal acceleration be? So for this, we're going to go ahead and take a look at the iPad screen just so we can work this problem out. So in part A, how long does it take the yo-yo to make 1 full revolution? What would be looking at here? How long? So we're looking for the period of revolution. Given our velocity of 36 meters per second, and also given that the string is 3 meters long, right? So our radius is going to be 3 meters long. What is the centripetal acceleration of the yo-yo, and how long does it take to make one full revolution? We can actually do both B and C at the same time, so I'm going to go ahead and include B in here as well. Our centripetal acceleration, A of C, is equivalent to our tangential velocity squared divided by the radius. So our centripetal acceleration is going to be 36 meters per second squared divided by our radius, which is 3 meters. So our centripetal acceleration, which is technically part B, comes out to be 432 meters per second, or meters per second squared. The next part of this problem, which would technically be part A, how long does the yo-yo take to make one full revolution? Here we have two different ways that we could go about this. We could look at our centripetal acceleration formula, the second one here, A of C equals 4 pi squared r over t squared. We could certainly use this one because we know our radius and now we know our centripetal acceleration. That was part of why I wanted to do part B first, was just to bring up this point that we could use 432 and the radius to find the period. But I'm going to go back to our tangential velocity, which is 2 pi r divided by t, because this is probably going to be a little bit easier for us to do. So by plugging in our values, we know v of t is 36 meters per second equals 2 pi times our radius, which is 3 meters, divided by the period. So when we rearrange this, we get the period is 2 pi times 3 meters divided by 36 meters per second. And this gives us a period of 0.524 seconds is what we get for our period on part B. Now if we come back and we look at part C and D, at what tangential velocity is it moving if we want the yo-yo to travel one revolution every 2 seconds, and what would the new centripetal acceleration be? So now for part C, what we need to look at here is the yo-yo making one revolution every 2 seconds. So our period, because this is time per revolution, we're going to complete, it's going to take 2 seconds to complete one revolution. As we see here, one revolution every 2 seconds. So our period is 2 seconds. We still have our radius of 3 meters. So our new tangential velocity, 2 pi r divided by t, we work this through 2 pi times the radius of 3 meters. Our time period is 2 seconds, so our tangential velocity comes out to really being pi times 3 because the 2's will cancel. So we get 9.42 meters per second is what we end up getting. And then part D, what would the centripetal acceleration be? So now our centripetal acceleration, because we know our tangential velocity and because we know our radius, I would use vt squared over r. We certainly could use 4 pi squared r over t squared. I just find the first one to be a little bit easier based on the information that we have. So our centripetal acceleration, vt squared over r, we use our new tangential velocity of 9.42 meters per second, and we need to square that. Divide that by our radius, which is 3 meters. And our centripetal acceleration will work out to be 29.6 meters per second squared. That is what we end up seeing for our values here. So again, There are those example problems worked out. Looking at those solutions there. As we finish up here, again, what's important to recognize is that the centripetal acceleration is always pointing towards the middle. It is always center seeking, which means it is always going to be perpendicular to the velocity, which will always be tangent to the circle.